And then after defining and giving you several examples, I think we have listed down some important properties, no? The things that homomorphisms preserve, like yung zero, yung um, negative, yung subrings, no? Kapag subring yung uh, pag subring ito ng R, yung image niya ay subring naman ng S. Yung mga ganong bagay, no? You will not be wait lang ha. I'm just checking on the previous slides. Kung ano yung ayun. I think dito tayo na natapos, no? Then there are, if you have a ring homomorphism F from R to S, there are two subrings which are of importance, no? Yung tinatawag nating range or image at saka yung kernel. Of course, yung range, it is nothing but the ordinary range of the function. Ang pag sinabing range, it's just a collection of all images of the things that are in R. So, kolektahin mo lahat ng mga images in the picture. Ito siya, no? Okay? Subring siya nung arrival space, which is S. On the other hand, or on the opposite end, may tinatawag tayong kernel. Ito namang kernel ay subring naman nung departure space, which is the R. Anong laman ng kernel? Yung kernel ay yung inverse image ng zero. When you say inverse image ng zero ng S, it contains all the things that are in R which are sent or which are mapped to the zero of the ring. So kung isipin mo, ang laman ng kernel ni F are the things in R that gets zeroed out kapag binap siya ng F. Yung sinizero ng F, lahat ng mga elements ng domain that gets zeroed out when F is being applied. Okay? Syempre, obviously, the range will tell us when is the homomorphism what do you call this? Onto. Pag onto, ang pangalan natin ay epimorphism, right? And we were able to prove that if the range or the image tells us kailan epimorphism ang isang ring homomorphism or onto, yung kernel naman on the other hand will tell us when is it one-to-one or when is the ring homomorphism a monomorphism. No? For the onto-ness, kailangan yung image mo, just like in this picture, kailangan yung image mo na to, it covers all of S para masabing onto. Para masabing one-to-one, no, according to this theorem, kailangan the only thing that is zeroed out by F or the only thing that gets annihilated by F, if you may want to use that term, no, is the zero of the ring. Kasi by default, the zero of the ring R goes to the zero of the ring S. So technically, si zero will always be zeroed out by F. So laging present siya sa kernel. The question is if there's some other elements aside from zero that is being zeroed out by F. Kung wala nang iba, maliban dun sa zero, ang zinizero ng F, we can say that the ring homomorphism is one-to-one or monomorphism. So in other words, kaya importante tingnan yung image at saka yung kernel because these subrings tell us the quality of the ring homomorphism as a function, if it's one-to-one or onto. Kasi kapag yung ring homomorphism mo naging one-to-one at onto, no, ang tawag na natin sa kanya ay isomorphism, no? Based on these notes, nagawa na natin yung proof nito last time. Ito yung proof, no? I was able to it's puro mga examples. Let's see. Describe the kernel and image of the following ring homomorphism. So at this point, I'm going to give you examples of homomorphisms, and we will look at the kernel and the image and maybe identify if based on the kernel and the image kung yung mapping ay one-to-one or onto or both. Let's see. The first example is the reduction homomorphism modulo D. How do you remember this? Ang ginagawa na ito, yung mu D of N is R. If and only if, paano nakukuha yung R? R is the remainder. When N is divided by D. So, naka-fixed yung value ng D, and then, paano malalaman yung image ng N? Kagaya nung definition niya, kukunin mo yung remainder when you divide it by N. We call it reduction homomorphism modulo D. So, as the image, anong itsura ng image ng function na ito? So parang we are asking because the images of the reduction homomorphism are remainders. So it's like we're asking, what are the possible remainders when you divide by D? No? When an integer is being divided by D. Of course, when you divide by D, ang mga possible remainders, it could be 0. You could have a remainder 1. No? In fact, the possible remainders are all this, no? From 0, 1, 2, and so on, hanggang D minus 1. Hindi pa pwedeng D. Wala tayong remainder na D. Kasi kapag D, naka-isang buong D ka ulit, so 0 yun, di ba? So basically, the image of this ring homomorphism is the entire ring Z sub D. Yan mismo yung laman ng Z sub D. On the other hand, when you look at the kernel, ang kernel naman, lahat ito ng mga integers from the domain kung saan ang mu D of n is equal to 0. So kung babasahin mo sa English yung definition ng mu D of n, di ba, siya yung remainder when you divide by D. So kapag sinabing ang mu D of n is equal to 0, what does that say? So this contains all the integers which leave a remainder of 0 when you divide by D. So basically, kapag sinabing remainder 0, ito yung mga integers n na dinidivide ng D. So ano laman nito? Ang laman nito yung mga multiples ng D. In abstract algebra, the way we write it is by doing the following. Okay? dz. Ang laman nito lahat ng mga multiples ng D. So as you can see, by looking at the image, by looking at the image, mu D is, we can say that mu D is onto kasi nagamit mo lahat ng mga elements ng arrival space as image. Pero when you look at the kernel, mu D is not one-to-one. No? Bakit kaya hindi siya one-to-one? Kasi maraming elements ito eh. Para maging one-to-one, dapat isa lang yung nasa kernel. Dapat yung tanging bagay na nasa kernel ay yung 0 ng ring. No? Pero maraming bagay na nasa kernel, so hindi siya one-to-one. So the mapping or the reduction homomorphism mod D is just an epimorphism but not a monomorphism. Therefore, it's not an isomorphism, clearly. Hindi naman talaga magiging bijective ito kasi tingnan nyo, ito infinite, kasi ito finite. So you don't expect this mapping to be a bijection, no? Kasi walang bijection ang meron from Z to ZD. At one point, either hindi yan magiging onto or magiging one-to-one. Right? Ina-expect na natin yun. Let's consider another example. Okay. Ano naman ito? Yung tinatawag na evaluation homomorphism, phi. Yung phi, so ang input natin ay polynomial na may real coefficient. And then, ang output natin, ang ginagawa natin, pag-evaluation, ini-evaluate mo yung polynomial at yung x doon sa polynomial, pinapalitan mo ng complex number na i. Yun yung ibig sabihin ng I doon. If you replace it by something else, mag-iiba na naman. No? Okay. So let's check kung anong kernel at saka image nung nung map na ito. Ano mo nung image niya? Basically naman nito, lahat ng mga P of I. Diba? So that P of X is a polynomial over R. So basically lahat ng mga evaluations na makukuha mo when you evaluate every real polynomial at I. Kung maaalala nyo, we have a notation for this. We denote this by R square bracket I. No? Ito yung lahat ng mga polynomials in I. But as you can remember, ito yung pinakamaliit na ring that contains R and the complex number I. No? And when you have a polynomial in I, let's say a0 plus a1i, a2i squared, and so on, a3i cubed, and so on. Ang mga powers kasi ng I paulit-ulit lang. I, negative 1, minus I, 1. I, minus 1. So, itong polynomial na to, kahit gaano yung kahaba, it simply simplifies into a plus b I. Kaya actually, yung R square bracket I na yan, yan yung field of complex numbers. Kasi yung A and B dito are arbitrary real numbers. Naintindihan nyo? As for the kernel, laman naman nito, mga polynomials in the domain, mga real polynomials, which when evaluated at I, it gives you 0. Sige nga. So this is quite a challenge. Now, paano nyo malalaman yung mga real polynomials which evaluates at I to 0? Can you give me an example? Anong mga real polynomial ang nag-evaluate sa I to 0? On the chat box or in the microphone, can you please give me examples? Pag-iisip kayo ng polynomial kung saan si I ay root. May tanong ako. Meron bang linear na polynomial kung saan si I ay root, tapos yung polynomial real? Hindi pa pwede, no? Di ba hindi? Hello? Nandyan ba kayo? O naka-on lang yung Zoom nyo? Type nga kayo ng 1 kung nandyan kayo. O, nandyan naman pala kayo eh. Ang tanong ko, magbigay nga kayo ng example ng mga real polynomials na kapag in-evaluate mo sa I, ang lalabas 0. Sikat na sikat yung polynomial na yan. Paano magiging 0 yung I? Sige nga, mag-scratch tayo. Sige. Paano magiging 0 yung I? Hindi yan magiging 0 pag nag-subtract ka ng, well, pwede ka mag-subtract ng I, pero bawal yun kasi kailangan ang subtract mo, ang i-multiply mo, real number kasi you're making a real polynomial. No? What you can do is you can square, kasi kapag in-square mo, negative 1. You can add a 1. So magiging, sige, ayun pala, may sagot na si Christian dun sa chat box. Sabi niya, you can take the polynomial x squared plus 1. Right? So actually, that's correct. X squared plus 1 is in the kernel. Right? But question, what are all the things that are in the kernel aside from x squared plus 1? Mapapansin nyo, kung meron mang polynomial na magko-contain sa, magsi-zero kay I when you evaluate, it always contains or it will always have x squared plus 1 as a factor. Kailangan lahat ng mga polynomials na may x squared plus 1. Di ba? As a factor. Kasi it's the only way you can zero out I. Kaya actually, ang laman na ito, lahat mga polynomials that are divisible by x squared plus 1. Okay? At kapag divisible ka sa x squared, at kung ito yung mga divisible sa x squared plus 1 as polynomials, in other words, ito yung mga multiples ng x squared plus 1. May pangalan kayo dito precisely. Ito yung ideal generated by x squared plus 1. If you can remember that. Pag sinabing ideal generated by x squared plus 1, because this is a commutative ring, ang laman nito, lahat lang ng mga multiples ng x squared plus 1. Halimbawa, x cubed plus x is there. No? Kasi this has x squared plus 1 as a factor. In fact, x to the fourth minus 1 is there. Kasi somehow yung x squared plus 1 makikita mo sa loob ng x to the fourth minus 1 when you try to factor, etc. Marami. Lahat yan ay elements ng ideal na yun. Okay? Naintindihan nyo? So, ito bang evaluation homomorphism? On to, yes. Is it one-to-one? Again, no. Sometimes mas mahirap maging one-to-one. No? Kaysa maging on-to. Sometimes. So kung napansin nyo dito sa example na to, yung kernel is actually an ideal of R square bracket X. Hindi naman yan, hindi siya nagkataon. It will always happen, no? As in the following theorem. If you get a ring homomorphism F from R to S, the kernel of F, kaya siya importante because it's a special type of an ideal of R. It will always be an ideal of R. Parang yung kaninang example ito. Ang naging kernel ng mu D, yung DZ. Eh, di ba yung DZ, ideal siya ng Z. It's a special type of a subring. Ay, sorry. Yan. More generally, kahit na anong ring homomorphism, when you look at the kernel, meron ka, parang to eh. Whenever you have a ring homomorphism from R, automatic meron ka ng magandang example ng ideal ng R. Just get the kernel of the ring homomorphism. In fact, lahat ng mga ideals ng R arise in this way. Ano ibig sabihin ni Sir ng ganon? Tingnan niyo yung second na claim, yung moreover. Sabi ko, tingnan niya, if I is an ideal of R, then there exists a ring T and a ring homomorphism psi from R to T such that the kernel of psi is I. What does that mean? Maliban sa alam natin na ang kernel ng homomorphisms palaging ideal, ang sabi pa nitong theorem na ito, lahat ng ideals ng R will arise in this manner. They will be kernels of a certain homomorphism from R. Did you understand me? Kumbaga, whenever you have a ring homomorphism, you get whenever you get a ring homomorphism from R, wala tayong pakialam sa S, no? Sa R. Whenever you get a ring homomorphism from R, you always get to have an ideal of R, namely the kernel. In fact, lahat ng ideal ng R are actually kernels of a certain homomorphism. So, parang sinasabi mo, parang sinasabi ng theorem na ito, is that kung gaano karaming ideals meron si R, ganon karaming ring homomorphisms ang pwede nating i-define. Kasi bawat isang ring homomorphism produces an ideal, and bawat isang ideal will produce a ring homomorphism. Did you understand? I hope you understand this theorem very well kasi this is a very important concept in abstract algebra. Alam niyo itong result na to is not exclusive for rings. This is also true for groups. This is also true for yun nga lang kapag groups, hindi ideals. Ang tawag natin dito normal subgroup. No? This is also true for vector spaces. Dito naman, subspaces ang mga usapan. Okay? Generally, this will be true for most of the types of algebraic structures in abstract algebra. Okay? So let's now prove the first claim. Why is the kernel an ideal of R? So first part tayo. The kernel of F is an ideal of R. How do you show that? Well, alam na natin na siya ay subgroup, di ba? We only need to show that it has the absorption property. Ano yung absorption property? Get an arbitrary element of the kernel and get an arbitrary element of the ring. Ang kailangan natin ma-prove dito, dapat yung RA tsaka yung AR are elements of the kernel, na-absorb ng kernel. Okay? By the way, since A is in the kernel of F, no, that means to say what? That means to say that F annihilates A. When you say F annihilates A, it takes A to the zero of S. So parang zero ni FC A. No? Kumbaga sa linear algebra, yung kernel, ang ibang pangalan natin dyan, null space. Ito yung mga vectors na sinizero ng isang linear transformation or ng matrix. Okay? So, how about AR? No? When you multiply AR, no, and apply F on AR, because F is a ring homomorphism, regardless of R, it will be F of A times F of R. But F of A is already 0. So regardless of R, this will always be 0. No? And even when you do RA, it doesn't matter. Magiging F of R times F of A, 0 pa rin. Therefore, both AR and RA gets annihilated by F. So they both belong to the kernel of F. So kung i-underline mo to, yan. Ano naging conclusion? Pag si A ay nasa kernel, si R is any ring element, yung product na AR tsaka yung RA will get absorbed by the kernel. So what does this prove? This proves that the kernel is really an ideal of R. Okay? Now let's prove the next claim. Sabi naman neto, if I is an ideal of R, makakahanap ka raw ng ring na T and a homomorphism psi from R to T such that the kernel of psi is precisely I. So basically, dalawa yung ipoprove natin dito na nag-exist, no? Yung una, ano yung ring na T? Pangalawa, ano yung homomorphism? So that's what we needed to that's what we need to produce in this theorem. Okay. So let's just write let I be an ideal of R. So ang kamay ng Diyos natin kukunin yung ring na yun at paano mo i-define yung homomorphism psi from R to T so that mapipilit mo na ang kernel ng ring homomorphism na to ay yung ideal na I. So how do we get that? Na ganito. Naalala nyo from previous lesson then I think kapag meron kang ideal na I, you can always construct the quotient ring of R modulo I. Ano naman ang quotient ring ni R modulo I? Ang laman nito yung mga cosets ng I. It's going to be a ring under coset addition and coset multiplication. So that's another way of forming a ring using the existing ring R and one of its ideals. No? Naalala nyo? Parang gumagawa ka ng mga copies ng I sa loob ng R. Parang ginugroup mo yung mga elements ni R into equivalence classes, into congruence classes, ang tawag natin. Di ba? Yun yung mga magiging elements, yung mga classes na yun yung magiging elements ng bagong ring mo. Ang gagawin ko dito, yung T, gagawin kong R modulo I, which is a ring. We know that this is well defined because I is an ideal. Remember yung R modulo I, magiging ring lamang only when I is an ideal. Okay? Paano naman natin i-define yung psi? Kasi we need to define ayan yung T natin, yung yung R mod I, di ba? Paano natin ito i-define? No? I-define natin to in a way na magiging homomorphism siya. Pangalawa, yung kernel niya ay I. Review. Anong elements ng R modulo I? Ang laman ng R modulo ay mga mga cosets ng ideal na I. Ano bang itsura? Pag sinabing coset, ano nga itsura? Ang itsura nun, parang si I lang yun, mag-a-add ka lang ng elements sa lahat ng elements ng I. No? So for example, A plus I, little a plus I, ng ganon. So, kapag meron akong R, saan kaya pinaka-natural i-associate yung R para maging coset siya ng I? Naturally, para mapunta ka doon, di ba, you can construct R plus I. Ito yung lalabas pag nag-add ka ng R sa lahat ng elements ng I. Yun yung coset na ito. No? So this will be our definition of psi. So let's prove that psi is what? Psi is a ring homomorphism at ang what do you call this? At ang ayun bang ginagawa ko? Wait a minute. Clear. Okay. Ang claim natin is that yung dinefine ko na function na ito will be a ring homomorphism at ang kernel niya ay si I. No? So we have the following claim. Psi from R to R mod I is a ring homomorphism. Okay? Paano? Kasi kuha ka ng dalawang elements ng R, let's say R and S. Kunin mo yung image ng sum. Okay? Now, paano ba yung image ng sum? Ano bang definition ng psi? Ina-associate natin dito yung coset ng I that contains R plus S. If you can remember, by definition, ito yung coset sum ng R plus I tsaka nung S plus I. which is technically psi of r plus psi of s. So therefore, psi is addition preserving. And hindi lang yun, it's also going to be multiplication preserving kasi ang psi of rs is rs plus I. If you can remember, this is the coset product of r plus I times s plus I, which in turn is equal to psi of r times psi of s. So check na yung claim na ito. Another claim is that yung kernel ng psi ay equal sa I. Yan yung kailangan mong i-prove pa further to finish the proof, no? But based on the definition, ano bang ibig sabihin ng kernel ng psi? Ang laman nito, mga bagay sa R that gets mapped to what? To the zero in this ring. The question is, what is the zero in the quotient ring R modulo I? Ang zero dyan, yan yung coset containing zero. Zero of R. I mean, that is yung 0 plus I. Or you can simply write I if you want. No? Sino yung 0 na to? Siya yung 0 ng R. Kaya lang, ano bang definition ng psi of R? Ang definition nito R plus I. Question. Kailan ba nag-i-equal ang dalawang coset? Equal ang dalawang coset if the representatives are congruent to one another modulo I. In short, kapag yung difference nila is an element of I. Yun yung ating definition ng congruence, di ba? So when you take the difference of the representatives, R minus 0 is just R. Kailangan yan ay nasa I. Okay? So kung titingnan nyo mabuti ito, tingnan nyo ha. Lahat daw ng mga ring elements ng R na nasa I, di ba yung I subset ng R? So yung set na ito, look at the set. These are the things in the ring that are in I. So technically, this is just I. Kasi basically si I ay subset ng R. And I think this completes the proof. Naintindihan nyo? Alam nyo may pangalan itong homomorphism na ito? We call it the canonical homomorphism from R kulang to. From, I should have written here from R, okay, tama pala yan. From R modulo I. It should be written this way kasi namali ako ng ano. Yeah. Kumbaga, itong homomorphism na tong ginagawa niya, ang claim kasi ng theorem, bawat ideal, bawat homomorphism from R produces an ideal, namely the kernel. In fact, every ideal is a kernel of some ring homomorphism from R. Yung some ring homomorphism na yun from R, yun yung canonical homomorphism from R. And if you want to emphasize that the ideal is I, you say modulo I. No? Okay? We have the following as a corollary. I don't know why this is a corollary. Let's see. Sabi nito, if you get a ring homomorphism F from R to S, this time, R is not just a ring, but it is a field. Ano yung sabihin ng field? Ano yung sabihin ng field? Commutative ring with unity, kung saan every non-zero element is a unit, or they all have multiplicative inverse as long as they are not zero. So yun ang sabihin ng field, no? Either, ano daw, si F ay yung zero homomorphism, or si F ay monomorphism. Aha. Para sinasabi nito, basta ang domain daw ay field, hindi masyadong marami yung homomorphism na pwede natin gawin. No? Ang mga possible na homomorphisms lang, kundi yung zero homomorphism. Pag sinabi zero homomorphism, ito yung homomorphism na pinapadala lahat sa zero ni S. Okay? Hindi masyadong marami. Either zero homomorphism siya, yung trivial one, or kung di man, dapat one-to-one siya. Okay? Why is that the case? Ganito. So let R be a field and F be a ring homomorphism. Okay. I want you to consider the kernel of F, which is an ideal of R. We have proven this many lessons ago, no? When we were talking about ideals and everything. Kapag field ang isang ring, hindi marami ang ideals niya. In fact, kapag si I ay ideal ng isang field, dalawa lang ang possibility. Either I is the entire ring, no? Or si I ay yung trivial na ideal or the zero ideal. May property tayong ganun dati. Kung babalikan niyo yung proof, ginamit yung fact na kapag ang ideal ay may unit, automatic, siya yung buong ring. Wala nang iba. Anyway, if you cannot remember, that is a property. Since R is a field, dalawa lang ang possibility sa I. Then either I is R or I is the trivial ideal. Okay? Kung si I o yung kernel ay yung R, then what can you say about F? Again, pag sinabing kernel, ito yung mga zero ng F. No? So kung ang kernel mo ay yung buong domain, ibig sabihin lahat ng mga nasa domain ay is zero ng F. So this means to say that F of R will be zero for all R in capital R. This means that F is the zero homomorphism o yung zeta na dinidenote natin. Okay? On the other hand, dalawa lang naman ang cases, either I is R or I is zero. If I is the zero ideal, then by the previous theorem, pag zero lang yung laman ng kernel, anong masasabi kay F? F is a monomorphism. So tatandaan nyo, whenever the domain is a field, kung hindi zero yung ring homomorphism mo, automatic one-to-one siya. Hindi ka pwede magkaroon ng non-zero na ring homomorphism from a field kung hindi siya monomorphism or one-to-one. Did you understand? So that's the proof. Okay? That's a corollary of the previous theorem, basically. So let's see. So we now have the following familiar theorem. If you were studying abstract algebra 1, or sa group theory, you might have heard the same theorem, but this one is in the setting of rings. We now have the so-called fundamental isomorphism theorem. Basically, yung fundamental isomorphism theorem, o yung ina-abbreviate ko by FIT or FIT, gives you the relationship between or how the kernel and the image interact with one another. Or basically, kasi ang mga kernel, mga ideals yan di ba, ng R. Basically, kung ano-ano yung mga possibility, ay hindi to equal. Nakita nyo, mali yung isomorphic ito. Isomorphic. I'm so sorry. Okay, kapag daw may ring homomorphism ka, of course, the kernel is an ideal. Therefore, you can form the quotient ring R modulo the kernel. No? It will be a quotient ring. It will be a ring isomorphic to whatever is the image. Okay? How do we prove this? Well, easy. Meron tayong actually madaling proof, no? Paano maging isomorphic yung R modulo the kernel to the image? So for simplicity, tuwagin na lang nating I yung kernel. Anyway, it's an ideal of R. Alam na natin yan. No? Kaya kung minimension na si I ideals, para legal, pwede mong kukunin talaga yung R modulo I. Otherwise, hindi mo pwedeng gawin yung quotient ring nang wala kang information kung ideal ba si I. Kailangan yun ay provided. Okay? Yeah, bakit isomorphic yung R modulo I sa image? So we need to construct an isomorphism from R modulo I to the image. Yeah? So how do we do that? Ganito. Define phi. So I'm going to use phi. Iba yung psi sa phi ha. Baka malito kayo. Define phi from R modulo I to the image as follows. Ano laman ng R modulo I? Ang laman ng R modulo I, mga cosets ng I. So typically, an element would look like A plus I for some little a in R. No? Question is, para mapunta ka doon sa image ng F, saan ko pwedeng i-associate yung phi of A plus I? To where should I define this, or to where should I map this one? Well, naturally, para mapunta ka dun sa image ng F, si A, little a ay nasa R, this is how I will define it. I will define it to be as F of A. In other words, I am basically using the definition of F to that A, apply F to A in order to be in the image. Kasi ang laman ng image, precisely yung mga elements na ganyan ang itsura. Would you agree? Yan. So, anong mga kailangang ipakita about phi? We need to show that phi is a ring homomorphism. Diba? Pero meron tayong problema. Ano na naman problema, sir? Ganito. Kasi yung domain ng function na ito, ang laman ay mga cosets. Remember, kapag cosets ang mga elements, there are many ways to write, there are many different ways to write a single coset. So, pwedeng meron ka isang coset pero marami siyang iba't ibang representation. Halimbawa, pwedeng yung A plus I pareha sa B plus I kahit na completely different si A and B. Hindi kailangang equal si A and B para ano. In fact, nag-equal yan if and only if A is congruent to B modulo I. Yan yung ating definition, di ba? And if you can, siguro, I'm going to just box this one. Kasi importante ito. Yan. Tapos maybe I could color this into yellow. Yan. So, ko ba ilalagay ito? Let's just put it. Sige na nga, dyan na nga lang. Hindi naman siguro istorbo yan sa inyo, no? Ayan. Tingnan nyo yung definition ng function natin. Yung definition ng function natin is representation dependent. When you say representation dependent, nakadepende siya on how you represent your coset. Kasi, halimbawa, pag ginamit kong representative si A, yung image niya is f of A. Ginagamit ko yung representative to determine the image. Paano kapag nagpalit ako ng representation? Let's say, ginamit kong representative si B. Instead of A plus I, ginamit ko B plus I. Di magiging image mo ngayon, f of B. Hindi ba mag-iiba yun, sir? Ito na naman tayo. Ang tawag dyan yung well-definedness. Naalala niyo to? Yung last time, no? We first prove that phi is well-defined. Ang ibig sabihin natin ng well-defined, na kahit na mag-iba tayo ng representative na pipiliin for the coset A plus I, you will arrive at the same image. No? Ganito. Suppose that A plus I equals B plus I. Okay? Then, of course, ano mangyayari? Yung, by definition, yung A minus B mo ay nasa I. Diba? Kaya lang, yung I, ano ba definition ng I? Si I yung kernel. So, pag nasa kernel ka, that means to say, zero ni F yung A minus B. And because F is a homomorphism, that means F of A minus F of B will equal 0s. Pag mag-add ka ng F of B on both sides, you will get the following. And therefore, by definition, yung phi of A plus I equals a phi of B plus I. You see? Ang importansya nito is that kasi nga cosets yung yung inputs mo, and then there are many ways to represent cosets. So, kung sakaling i-represent ko siya differently, let's say using B plus I, hindi ka naman pala matatakot na mag-iiba yung image. Although f of B lang yung itsura ng image, but basically f of B na yun tsaka f of A, parehas lang. Naintindihan nyo? Therefore, phi is well-defined. Okay? Second, bakit siya homomorphism? Madali ito. Bakit siya homomorphism? Kasi when you, ano nga ulit definition? Let me just rewrite it down. Phi of A plus I is defined as F of A. Okay. Pag meron akong dalawang coset, kuha ka ng dalawang cosets kasi ang domain nito R modulo I na. So just get two cosets. Let's say A plus I plus B plus I, i-add kong ganyan. Yan. By definition of coset addition, this is A plus B plus I. And by the definition of phi, kukunin mo yung representative, i-apply mo si F. But given na si F ay ring homomorphism, so parehas sa F of A plus F of B. Kaya lang, sino ba si F of A? Siya si phi of A plus I. Si F of B naman, siya si phi of B plus I. So as you can see, phi is addition preserving. In a similar manner, it will be multiplication preserving as well. No? Paano? By definition of coset multiplication, this is AB plus I. And by the definition of phi, this will be f of AB. Eh kasi nga, kung nga si f ay ring homomorphism, you can use the fact that it is a ring homomorphism, so you can write this. So ito yung phi of A plus I times phi of B plus I. So therefore, phi is a ring homomorphism, a well-defined ring homomorphism. Ang kailangan natin ay isomorphism. In fact, ito yung isomorphism na gusto natin. So in order to show that it is an isomorphism, what? You only need to show that it is what? 1-to-1 and 1-to. Trivially, phi is onto. Bakit trivial ito? We don't need to prove that anymore. Kasi ang itsura ng images niya, mga f of a, eh ang laman ng image ng f, talaga naman yung mga f of a. So trivially, yung image nung nung phi ay yung image din ng f. 'Di ba? So hindi yun question, right? Ang question dito yung pagiging 1-to-1. Now, how do we show that phi is 1-to-1? Because phi is a ring homomorphism, we can apply the previous theorem once again. You might want to look at the kernel of phi. Hindi nung f nung phi. Kailangan ang nandun lang sa kernel ay isang bagay lang. Okay? So let's try to move to a new page. Clear ko lang to. We only need to show that phi is 1-to-1. Okay? By looking at the kernel, ano ba yung kernel ng phi? Ang definition ng phi as well. Ang definition ng phi, well, ang domain niya mula dito papunta doon. Okay? O sige, tingnan natin. Ang kernel, ang laman, mga cosets mula doon sa right? Mula doon sa R modulo I, so that ang phi of A plus I is equal to the 0 in the image. Eh yung image, subring lang yan ng S, kaya ang 0 niya, yung 0 lang din ng S ha. Kaya ito, sulat mo 0, S. Eh, ano bang definition ng phi of A plus I? Well, F of A lang ito. So, tingnan nyo. Ang laman ng kernel ng phi ay yung mga A plus I where F of A is equal to the 0 in S. But this equation implies that anong ini-imply niyan? Yung A ay nasa kernel ng F. Eh kaya lang ang kernel ng F, siya mismo si I. Kaya, ang laman nito mga A plus I where A is in I. Eh di ba kapag si A ay nasa I, saan equal yung A plus I? Parehas lang yun sa 0 plus I. Diba? Kaya ang laman lang yan, 0 plus I, wala nang iba, which is the 0 of R modulo I. Therefore, now we can conclude that phi from R modulo I to the image is 1-to-1. Therefore, phi from R modulo I to the image is an isomorphism. And therefore, because may isomorphism ka from R modulo I to the image, R modulo I is isomorphic to the image. But what is that I again? Siya yung kernel. Okay? So we were able to prove that the fundamental isomorphism theorem. Bakit kaya ito tinawag na fundamental isomorphism theorem? Well, kasi marami itong applications in the future. No? Makikita nyo whenever we wanted to prove something is isomorphic to this, most likely, especially when speaking of quotient rings, no? Most likely gagamitin natin ito. Technically, ito yung nangyari. Okay. Ito si F. F is a ring homomorphism from R to S. Let's say ang kernel niya ay I. Okay? Naalala niyo yung psi? Yung psi is the map from R to R modulo. Ayun yung canonical isomorphism. Oh, mu pala ang ginamit ko dito. Well, sa atin kasi sa proof, ito yung phi, hindi mu. Phi ang ginamit ko, hindi mu. Yung phi doon sa proof kanina, siya yung map from R modulo I to the image. Just in case yung image mo ay yung S. Right? So parang ito yung diagram, yung pinagkaiba-iba ng F, ng psi, tsaka ng phi. In fact, yung F ay yung composition ng mu, tsaka ng psi. Right? This is just an abstract representation. Balikan natin yung mga nakaraang example natin. Ano, mamaya na yan. Mamaya na itong dalawa. Mamaya na yung dalawa ha. Ano, balikan natin ito. Ano nga ulit ang kernel nito? Yung DZ. Ano yung image nito? Yung buong Z sub D. So by the fundamental isomorphism theorem, yung Z modulo DZ daw is isomorphic to the ring Z sub D. Did you understand that? Talaga naman, di ba? Yung Z modulo DZ, ito yung mga cosets ng DC, they form a ring isomorphic to Z sub D. So that's what the fit is telling us. So when you're using the evaluation homomorphism, phi, naalala nyo, ang kernel nito is the ideal generated by x squared plus 1. At ang image niya ay si C. Fit now implies that when you take the quotient ring of R squared bracket x modulo the ideal generated by x squared plus 1, it's going to be isomorphic to what? To C. Parang familiar ito. Sa nakaraang lesson, if you can remember, itong ideal na ito, maximal ideal siya. Kaya yung quotient ring na ito will be a field. In fact, yung mga elements nito, yung mga cosets na nandito, if you can remember, they behave like complex numbers. In fact, hindi pala nakakagulat yun kasi the quotient ring is really isomorphic to the field of complex numbers. So if you may allow me to go back to that example once again, hanapin natin ha. Wait lang. Hanapin ko yung example na yun. Wait. Pinabalikan ko yung previous na slide where it shows that example. Okay, no? Do you remember this? Ayan. In this ring, yung x squared plus 1, congruent siya sa 0 modulo I. Kaya ang x squared, congruent sa negative 1 modulo I. Pag nag-a-add ang mga elements na ito, if you can remember, may be expressed using the division algorithm, they may be expressed as a plus bx plus I. So pag nag-a-add ka ng dalawang ganyan, para ka lang nag-a-add ng dalawang complex numbers. Pag nag-multiply ka, para kang nag-multiply ng dalawang complex numbers. Kasi yung x squared dito, napapalitan mo ng negative 1. If you can remember this. Parang complex number multiplication at addition. Ngayon natin na-confirm, no, na really, Wala pala talagang difference kasi actually may difference, hindi sila parehas, pero they represent the same algebraic structure, namely the field C of complex numbers. Okay? Ayun, yung elements ng ring na ito, mga ganito, mga cosets ng I na ganyan ang itsura. Whereas yung elements ng C ang itsura, A plus BI. Kumbaga, ito yung C, the way you first knew it, no? Pero in some multiverse, no? Pag pumunta ka sa ibang parallel universe, ganito itsura ng mga complex numbers. They represent the same thing. They may be different in form, but they represent the same algebraic structure. No? Ngayon lang natin na-confirm na talagang isomorphic siya sa C. Kasi ngayon lang naman tayo nagkaroon ng concept ng isomorphism. Di ba? Okay. Pabalikan ko yung previous na slides. Itong dalawang to are basically applications of the fundamental isomorphism theorem. Magbibigay na lang ako sa inyo ng notes about these two. Ito ginagamit sa group theory. Most likely sa group theory ito nagagamit. Pero sa rings, ito siguro nagagamit pero we will not use them anyway. Ang gagamitin ko lang in future discussions are the fit. Yung fit lang. Ito, nagagamit ito. For example, itong isomorphism theorem na to, yung tinatawag na diamond isomorphism theorem. Kaya siya tinawag na diamond kasi when you look at this lattice diagram, yung I plus J, siya yung pinakamaliit na magko-contain sa I and J. Yung intersection, siya naman yung pinakamalaki that is contained in both I and J. No? If I and J are ideals daw, no? Ideals din ito. When you form the quotient ring I plus J modulo J, at ginawa mo yung ring na I modulo I intersection J, they will be isomorphic as quotient rings. Kaya tinawag na diamond kasi may diamond dyan. Ito naman, tungkol sa dalawang quotient rings ng R. May ideals ka ng R, J, tsaka I, kung saan si I nasa loob ng J. So therefore, mas maliit si I, mas marami siyang cosets kaysa doon kay J. Kasi mas malaki yung ideal mo, mas kaunti yung coset ng remember, ang mga cosets, mga copies yan ng J na pumupuno doon sa R kasi partition yan ng R. So mas maraming elements ito kaysa dito. In fact, yung R modulo I, ano bang gusto kong sabihin dito? And then you can also consider the quotient ring J modulo I. It turns out that J modulo I, kasi parehas cosets ng I ang laman nitong dalawang yellow, di ba? You look at the two yellows, pare-parehas cosets ng I ang laman nila. It turns out that J modulo I is an ideal of the quotient R modulo I. Kaya double quotient kasi kumukuha ka ng quotient ng dalawang quotient. Well, itong theorem na ito only says na wala ka namang mapapalang bago when you take quotients of quotients. Kasi when you take the quotients of two quotients, it's nothing but another quotient of R, namely R modulo J. Kumbaga, hindi bagong structure yung magagawa mo when you do quotients of two quotients. Kumbaga, ito ini-state lang for the sake of abstract questions such as that. No? Meron bang maproproduce na bago when you take quotients of two quotients? Ang sabi ng theorem nito, wala namang bagong maproproduce kasi ang maproproduce mo lang is a ring which is just another quotient ring of R. Kumbaga, nandun na rin siya dati pa. Did you understand? Yun lang naman yan. Just another note, yung diamond isomorphism theorem. This is related to the so-called, what do you call that? Yung GCD-LCM theorem. Kasi kapag nasa number theory ka, Let's say meron kang AZ tsaka BZ. Ano yung pinakamaliit na ideal ng Z na magko-contain sa dalawa? Sinabi ko na yan dati, DZ. Yung D dito, GCD ng A and B. Yung intersection naman nila, ito yung LZ, kung saan si L ay LCM ng A and B. Right? Right? Okay. So, ang sinasabi nito, yung DZ modulo BZ is isomorphic daw saan? Sa AZ modulo LZ. So, kapag bibilangin mo, so kung isomorphic yan, sabihin mo kasing dami sila ng laman. Finite yan eh, itong mga to. Finite yan. Dapat magkasing dami ng laman yan. Kung bibilangin mo kung ilang cosets meron, nagdi-divide tayo. No? Ilang cosets meron si BZ sa loob ng DZ? Halimbawa, ilang cosets meron si 4Z sa loob ng 2Z? Kasi ang mga multiples ng 4, multiple din naman ng 2. Diba? Oh. Masagot dalawa. Ang mga cosets yan, si 4Z tsaka si 2 plus 4Z. These two comprise all the things which are divisible by 2. Ang formula, dinidivide 4 divided by 2. Kaya dito, kung ilang cosets meron, ang sagot, B over D. Dito naman, L over A, baligtad. So when you simplify, you will get AB equals D times L. So ano sinasabi nito sa number theory? Ang implication nitong isomorphism theorem na to sa number theory is that ang product ng GCD tsaka LCM ng dalawang integers ay parehas dun sa product ng dalawang integers. Theorem yun sa number theory, but it is an easy corollary of this diamond isomorphism theorem. Halimbawa, meron kang dalawang integers, kunwari si 12 tsaka si 8, no? Anong GCD nila? Ang GCD nila ay 4 obviously. Pero ang LCM nila, ano yung LCM nila? Anong LCM ng 12 and 8? Paki-chat na sa chat box. (24). Okay. Ang sinasabi ng theorem na ito, ng diamond isomorphism theorem, yung product daw ng dalawang integers ay pareha sa product ng GCD tsaka ng LCM. Is this correct? Yes or no? Correct ba? 12 times 8 ba para sa 4 times 24? Oo, no? Kasi hiramin mo yung 2 ng ng 24, 8 times, yeah, correct. Yun yung sinasabi ng diamond isomorphism theorem. When you translate it into a number theoretical result. Okay? Nasaan na ba tayo? Tapos na tayo dito. Right. Let's now consider a commutative ring with unity. Let's call it R. Magde-define ako ngayon ng function from Z, the standard integer set, to the arbitrary ring R. Ang gagawin ko ganito. Pag sinabi kong f of n, kasi n ay integer, no? Ang gagawin ko, i-multiply ko yung n sa 1. Ano yung sabihin ng 1 dito? Huwag kayong papalito dito. Ha? Yung 1 dito, siya yung unity ng ring. Imagine niyo kunwari si R, mga matrices ang laman. So yung 1 dyan ay identity matrix. Pero yung n ay integer. Kaya yung n times 1 dyan, parang kapag sinabi 4 times I, ang sabihin yun, I plus I plus I plus I. Naintindihan niyo? Okay. Kumbaga, yung 1 dito, hindi siya number. Siya yung ring element, that is the unity, the identity element for multiplication. Ang number dito yung n. So this function f converts the integer n to a ring element. Paano, sir, kapag negative yung n? Halimbawa, f of negative 3. Ano yung sabihin natin ng negative 3 times 1? May definition tayo na ito dati, if you can remember. This is the additive inverse of 1 added to itself 3 times. Yun yung sabihin natin ng f of negative 3. Did you understand? Okay. You can check that f is a ring homomorphism kasi pag meron kang dalawang integers, n1 and n2, when you add, this is n1 plus n2 times 1. Ang ibig sabihin niyan, gagawa ka ng kopya ng 1, n1 plus n2 times. So parang ganito, 1 plus 1 ito n1, ito n2. Kaya you can write it as n1, 1 plus n2, 1. Kaya meron kang f of n1 equal plus f of n2. So si f ay addition preserving. Correct? It is also multiplication preserving, although this is harder to prove. Kasi when you check n1, f of n1, n2, this is n1 times n2 times 1. No? So parang 1 ito na uulitin mo ng ilang beses? n1 and n2 times. Okay? Wait lang. Nakikita niyo ba yung screen ko? May tumawag kasi bigla sa akin. Nakikita niyo yung screen ko? Do you still see my screen? Okay, thank you. Ito, hindi lang halata, pero parehas yan sa product na ito. Using distributive property, meron kang n1 na 1, dito may n2 na 1s ka. Kasi kapag nag-distribute tayo, di ba, yung bawat isang 1 dito, tina-times mo sa n2 na 1s. Diba ito, ilang terms ang ma-generate mo? n2. No? Bawat term dito will produce n2 terms. Ilang terms ba ito lahat? n1. So ilang 1 lahat yung product na yan? n1 times n2. Parang halimbawa, meron akong 1 plus 1 times 1 plus 1 plus 1. Kapag ito in-expand ko, pag ganito, ilang 1s yung maproproduce? 3. Pag ganito, ilang 1s na maproproduce? Another 3. Nakailang 3 ka? 2. Kaya 2 times 3, which is 6. Did you understand? No? Kaya ang lumabas, ito ngayon yung f of n1 times f of n2. Kasi f ay multiplication preserving din. Okay? Ayan pala. Meron pala akong paliwanag dito why that happens. Okay? Let's see. Do you remember the chi? The chi is not the chi as in statistics chi-square, no? The chi here represents the characteristic. Ang characteristic ng ring, siya yung pinakamaliit na positive integer kung saan pag si 1 inad mo sa sarili niya ng that number of times nagiging 0. Pero kung hindi nagsi-0 yung 1, pag inad mo ng inad, ang characteristic niya ay 0. Okay? So kapag ang characteristic ng R ay 0, ibig sabihin nito, yung 1 nung ring na yan, pag inad mo ng inad sa sarili niya, never babalik sa 0. Okay? So the question is, what is the kernel of F? Kung hindi ito babalik sa 0, kailan magsi-0 to? Kasi di ba ang kernel, na alam natin kailan nagsi-0 ito? So the only way for this to be 0 is when n is precisely 0. Kaya ang kernel mo ay singleton 0. Ano naman ang image mo? Ang image mo naman, lahat ng mga multiples ng unity, which is a subring of R. Right? Right. So, anong sinasabi ng fit? The fit implies that Z modulo the kernel is isomorphic to the image. But Z modulo the kernel, or Z modulo 0, is just isomorphic to Z. Naturally, kasi kapag 0 yung ideal mo, ipapartition mo lang yung Z into singletons. So basically, parang kahawig lang din siya ng Z. Anong sinasabi nito? Yung image ng F, of course, nasa loob ng R yan, no? Ay isomorphic sa Z. Ibig sabihin, parang si R ay mayroong subring na isomorphic sa Z. Understand? Kapag si R ay may characteristic na 0, ang naging conclusion, si R ay mayroong subring na isomorphic sa Z. On the other hand, kapag naman positive ang characteristic ng R, halimbawa ang characteristic ay M, ibig sabihin ng characteristic na M, pag naka-M na ones ka, nagsi-0 na. Ang tanong, anong laman ng kernel? Ang laman ng kernel, kada M, nagsi-0 yung, yung 1 plus 1 plus 1, di ba? Yung f of n, I mean, nagsi-0 to kada M. So, tuwing kailan to magsi-0? Magsi-0 yan kapag M, kapag 2M, kapag 3M, kapag 4M. In short, kapag multiple ka ng M. On the other hand, the image also consists of this is a subring of R. And again, by fit, ito yung mangyayari. Yung Z modulo MZ, which is the kernel, is isomorphic to ZM, di ba kanina? Na-establish natin to. At isomorphic siya sa image na sa loob ng R. Ang nangyari ito. Ito nangyari. Pag ang ring, ang characteristic ay 0, meron siyang subring na isomorphic sa Z. Kapag ring ay may positive characteristic na M, yung ring ngayon may subring na isomorphic sa Z sub M. And we have the following very nice property. No? Kapag daw si R ay ring with unity, kung ang characteristic, kulang to ng commutative. Kung si R daw ay commutative ring with unity, dalawa lang naman ang cases, kundi 0 ang characteristic niyan or positive. Kung 0 ang characteristic ng ring mo, hindi man siya isomorphic sa Z, meron siyang anak or meron siyang within itself na kamukha ng Z. How nice is that? No? Parang basically, ang mga rings mo, basically, nakatungtong lang sa dalawang bagay. Kundi sa Z sub M. May sabihin ko ng, ganito ha, hindi ko sinasabi na lahat ng ring ay extensions ng Z tsaka ng Z sub M. Ang sinasabi ko, kung ito si ring mo, ng commutative ring with unity, meron siyang subring na hindi ko sinasabing equal sa Z, rather, this is isomorphic to Z kung yung characteristic niya ay 0. Kung ang characteristic naman ay M at yung M na yan ay positive, yung magkakaroon ka naman daw ng subring na isomorphic sa Z sub M. This is a very nice theorem kasi we were able to tell this to any kind of commutative ring with unity. Ano naman sinasabi niyan kapag kapag si F ay field? Ito naman yung versions niya kapag si F ay field. Ang characteristic naman ng field, kung di 0, if you can remember, kung di 0, prime. Hindi pa pwedeng hindi prime ang characteristic kapag field kasi integral domain yan. If you can remember. So, kapag ano naman, meron namang subfield si F na isomorphic sa Q. Siyempre, kapag characteristic naman niya ay P at yun ay prime, kagaya nung nakaraang argument, si F naman ay may subfield isomorphic to Z sub P. So parang ang mga commutative rings with unity natin, parang nakatuntong lang sa dalawang possible cases. No? Either meron siyang Z within it or Z sub M within kung commutative ring with unity. Pero kung field ka naman, nakatungtong lang din siya sa dalawang possible na cases. Either there is a structure of Q within it or a structure of Z sub P within it. Did you understand why these things are so important? Kasi nagbibigay tayo ng general structure for an arbitrary rings and field. Okay? What's next? Tapos na yung slides na ito. So let's move on to the next set of slides. Sa lesson na ito, ano bang pag-aaralan? Pag-aaralan natin yung tinatawag na reducibility of polynomials. Ang reducibility na word, ano lang naman yan? It's a fancy name of polynomials being factorable. Ang ginagamit yung term dati, factorable. Pag sinabing factorable, it can be split into two smaller pieces as factors. No? Pero pag tayo na sa abstract algebra, we don't use the word factorable, rather we use the word reducible. Okay? Let us now give some introduction. Alam niyo naman, no, kapag nagmumultiply ng dalawang polynomials, hindi siya madaling problem, especially when two polynomials are have several terms and big degrees, no? Hindi man din mag-multiply ng polynomials. Pero yung problem ng multiplying polynomial is systematic. Meron tayong step-by-step procedure. No? Pwede yung distributive property o yung method natin ng parang table, no? Kahit na hard siya, it's not that hard kasi meron tayong systematic na paraan. Pero, ang totoong problema ay factoring kahit naman sa integers, di ba? Kahit naman sa integers, madaling mag-multiply ng dalawang integers kahit gaano yan kalaki. Hindi ko sinasabing madali as in mabilis gawin ng kamay. Ang sinasabi ko, we can ask the computer to we can create a program, ask the computer to multiply two integers kahit gaano yan kalaki, makakagawa ka ng algorithm. But the real problem is the reverse. Parang nire-reverse engineer kasi natin to. No? Parang, paano mo i-split? Let's say, alam mo yung product. Paano malalaman yung factors? Well, madali siya kapag siguro nagagawa natin ito ng mga maliliit tayo kasi yung mga numbers na kino-consider sa classroom are relatively small. No? Hanggang ano lang, karaniwan hanggang 4 digits, di ba kapag elementary school, never kayong makakakita sa classroom ng malaking product. Bakit ito issue? Kasi alam niyo ba yung mga crypto systems natin na ginagamit to encode data, decrypt and encrypt data sa sa mga ATM, sa mga credit cards, yung mga codes diyan. Alam niyo yung yung encryption procedure niyan gumagamit ng dalawang prime numbers. Yung dalawang prime numbers na yun are chosen to be very big. Kumukuha tayo ng dalawang prime numbers na malaking-malaki and then multiply yun ng computer together. So you get the product of these two prime numbers, right? And then, gamit yung product na yun, i-encrypt natin yung information from the credit card, maybe your credit card numbers or ATM cards, no? Para kapag transmit sa internet, hindi siya, kung ma-hack man yung information, naka-encrypt siya. Now, syempre, hindi ka gagawa ng encryption process nang hindi mo kayang i-decrypt. No? Syempre, ang makaka-decrypt lang ng information mo ay yung computer na alam kung ano yung dalawang malaking prime number na yun. No? The reason, alam niyo yung safety ng yung safety ng encryption decryption process niyo kapag nagpapasok kayo ng ATM sa ATM machine, ATM card sa ATM, nakadepende siya sa hirap ng factoring ng dalawang polynomials. Kasi kung madali polynomials, prime numbers. Kasi kung madali mag-factor ng isang integer into two primes, edi ma-hack lahat. No? Pag kasi kumuha ka ng dalawang malaking prime number, madaling i-multiply yun. Pero kung paano mo siya hahatiin sa dalawang prime number ulit, it's not an easy process, especially when the prime factors are large. Kaya sa mathematics, it's always an issue, no? To know kung ano yung mga pinakamalalaking primes kasi we are using them in modern computers, no, to encrypt data. Yung pagiging mahirap ng factoring, actually napapakinabangan natin yan to encrypt the data kasi even the computers, even when you ask the computer to check if this is a factor of that, like that, no, mahirap siyang i-program at hindi yon madali. It will take the computer a large amount of time to be able to decrypt that. No? Ang tawag dun sa sinasabi kong encryption process yung RSA public key cryptography. No? Similarly, ganun din kapag polynomials. No? Madaling mag-multiply, pero it's even, sabihin na natin mahirap mag-multiply, pero it's always even harder to factor a polynomials into factors. No? Ito yung mga tanong na titignan natin in the next few lessons. Pero ano po masasabi when is a polynomial factored completely? And if a polynomial can't be factored, parang prime number ito, no? If a polynomial can't be factored, how can we know that in advance? How can we know that it's not factorable? Or parang in the case of prime numbers, if you just look at the number, how would you know that it is a prime? Same. Nga lang dito, ang context natin ay polynomials. Okay? If you can remember, the units of z are 1 and -1 only. So, these are the only things that have their multiplicative inverses. Remember, an integer n greater than 1 is called prime. So, technically, basically, by a prime, automatic, hindi kasali yung 1, no? Excluded kagad yun kasi by definition, n is greater than 1. This should be, siguro dapat p ito. Mali si sir, siguro dapat yan p. An integer p greater than 1 is prime if and only if whenever you split p into two factors a and b, either a is plus or minus 1 or si b ay plus or minus 1. So this is one way to characterize prime numbers. Okay? In short, kapag si prime ay in-split mo into two factors, dapat yung isa sa mga factors ay unit. Yan lang naman ang gusto kong sabihin dito. Kasi ang mga units ng z are plus or minus 1. If D is an integral domain, the units of D square bracket x are precisely the units of D, right? Yung underlying ring when we view them as constant polynomials. Therefore, we have the following definition. Dito natin hinango yung term na irreducible sa definition ng pagiging prime. Ang prime kasi may property, prime number. Pag in-split mo siya into 2 factors, dapat yung isa dun unit, 1 or negative 1. Kasi diba, 7. What are the different ways to factor 7? Well, it's 7 times 1. Pwede rin naman negative 7 times negative 1. O, diba? In either of this factorization, palaging yung isa unit. Okay? So here, D represents an integral domain. So you get a polynomial in the integral domain D square bracket x. So automatic, hindi na natin kino-consider yung 0. Ayaw din natin na unit siya. So dito diba gusto natin hindi siya unit. So parang ganun din. So P of x is non-zero and non-unit. Bawal 0, bawal ang unit. So we say P of x is irreducible over D. Ito yung hindi na ma-factor. If whenever you force factor it into A of x times B of x, then certainly one of A of x or B of x is a unit. Ano ba yung unit sa D square bracket x? Ang unit sa D square bracket x ay yung mga units lang din sa D. Sabihin mga constants lang to na na may multiplicative inverse. Otherwise, kung hindi ito totoo, if it is possible to factor this so that both of these are non-unit, then P of x is reducible over D. Ang kabaliktaran ng irreducible ay reducible. Ang dinefine natin ay irreducible. So, gamit yung definition ng irreducible, yung negation niya, tinawag natin reducible. Nire-write ko lang naman. May mga comments lang ako. So, in the case when F is a field, kasi pwedeng ang field naman integral domain din. The units are precisely the non-zero elements or the non-zero constant polynomials. Kaya kapag field yung usapan, pag sinabing reducible yung polynomial, ibig sabihin nun, pwede mong i-express si P of x as a product AX, BX, where yung AX at BX na to, ang mga degrees nila mas maliit sa P, degree ng P, at parehas positive ang degree. Sabihin, walang constant polynomial sa kanila. Okay? Ito, ina-ensure na hindi constant yung A of x, B of x. Ito naman, ini-ensure na kasi pag yung isa sa kanila, ang degree ay kasing laki ng P, yung isa mapipilitan maging constant. So, nire-require natin ito. Kapag ganito yung itsura ng reducible, kapag field ang usapan. Okay? Pero don't worry, most of the times naman, we will be dealing with fields. Pero sometimes, we also deal with non-fields. Halimbawa, is this polynomial reducible over Q? What do you think? Q is a field. So, ang tanging option mo na lang ay what? Ang tanging option na lang natin ay dalawang linear. Diba? Bawal kasi yung constant yung isa. So, can parang ang tanong dito, can we write as a product of two linear polynomial like this? Where A and B, C are not zero kasi kailangan linear. Diba? What do you think? Eh kapag sinubukan mo, i-multiply, get AC x squared, you get AD plus BC x plus BD. Tingnan nyo. So, kung equal siya sa x squared minus 2, that means AC is 1, AD plus BC is 0, at ang BD ay negative 2. Oh, I don't know kung anong gagawin ko. Kailangan makahanap tayo ng contradiction if we want to say no. No? Ano kayang i-imply niyan? Ano kayang manipulation ang pwede niyong gawin? So, hindi 0 si, ano no, si A? Hindi 0 si A, hindi rin 0 si C. What does that mean? Hindi ko rin alam. Pero alam natin kasi by intuition, yung x squared minus 2, hindi yan ang factor, di ba? Into linear factors. Tama. Kasi the way to factor this really is by doing the following. Di ba? Kaya hindi nga lang kasi mga rational numbers yun. Pero you have to show that a contradiction will uh, emerge kapag nangyari ito. Paano kaya ang contradiction dito? I'm also looking at that. Pag sabay-sabay naging true ito, bakit may contradiction? Well, let's see. Ang AC ay 1. Oh, wait lang. Dito, ang AD ay equal sa minus BC. So, ang D mo, when you look at D, I can write it as BC over A. I can divide by A because I know that A is not 0. So, when I use this equation to substitute there, ang BD is negative 2. So, B times minus BC over A is what? Is negative 2. That means B squared C over A is positive 2. No? Tama ba? Tapos, wait. Yan. From A equals 1, ang C mo kasi ay 1 over A. So from that, ang mangyari, B squared over A squared equals 2. Ang mangyayari, B over A squared is equal to 2. This is a contradiction. You know why? Because there is no rational number whose square is 2. We have proven that a number of times, even in earlier courses in mathematics. So babagsak ka sa pagiging irrational ng square root of 2 kasi. Na? Pag kasi itong tatlong equation na to ay nag-hold, magkakaroon ng rational na square root yung 2, which is not the case. We know which is not the case. So ang tanong din, ang sagot dito sa tanong na to, can we write this as a product of two linear factors? The answer is no, because we were able to arrive into a contradiction. So parang nag-algebra lang to. No? So the answer is no. Ang tanong, is x squared minus 2 reducible over r? Yes, no? Kasi this time, yung x squared minus 2 can now be written as x minus square root of 2 times x plus the square root of 2. So dito kanina, no. So ano mapapansin nyo? Ang pagiging reducible ay hindi masasabi kung hindi mo i-specify kung saan. You have to specify over which ring are we talking about. Are we talking about reducibility over Q or reducibility over R? Kasi sometimes, polynomials are reducible over R, pero hindi siya reducible over Q. No, that happens. Did you understand me? Did you understand? Sige nga, can you chat 1 kung nakakasunod? Okay. Salamat dito sa mga masisipag mag-chat. Kasi sometimes nakaka-discourage magturo pag wala kang naririnig na anything. Itong polynomial na to, yung x squared plus 2, we know that it is irreducible over R, but reducible over C. No? In fact, yung x squared plus 2, huwag na natin isa-isa. No? Ito ay, paano ba to? X minus square root of 2i, x plus square root of 2i if I do it correctly. Tama ba ako? Yeah. This is a correct factorization. So, na-reduce natin siya sa C, but it is not possible to reduce it over R. How do you show it? How do you show that? Gawin nyo yung ginawa ko kanina sa Q. Kunwari, ma-factor ulit sa x squared plus 2 into 2 linear factors. Show that, what do you call this? Show that a contradiction will emerge, no? If you assume that. Okay? Ito, itanong ako. This is now different. Kasi si Z ay hindi naman filled. Pag hindi filled yung ring, you have to go back to the original definition. Ito ba ay reducible over Z? Ulit. Pag irreducible, whenever you can factor it into two factors, yung isa, unit. Okay? So, kapag sinabing irreducible, it is not possible to, kapag reducible, it is possible to factor the polynomial into two non-unit polynomials. So, ito ba irreducible over Z? Itong 2x squared plus 4, alam nyo, ano to eh? Obviously, that's 2 times x squared plus 2. Tama ba? Question. Is x squared plus 2 a unit in Z? Square bracket x. No, hindi naman, no? Walang reciprocal yan. Kasi ang tanging units ng Z square bracket x are the units of Z, which is 1 or negative 1. How about the other factor? Is 2 a unit in Z square bracket x? Hindi rin naman. So therefore, in this case, this is a non-trivial factorization over Z. So the answer to this question is yes. Kasi yung 2 dito, hindi siya unit over Z. Naintindihan nyo? I was able to factor 2x squared plus 4 into 2 so that both of the factors are non-unit. Nagkataon kasi sa Z, si 2 ay hindi unit. Ang units nga lang kasi sa Z ay 1 or negative 1. Kumbaga, kapag ang ring na pinag-uusapan ay Z, nagmamatter yung factorization na to. Kumbaga, this is not a trivial factorization. Pero, kung ang tanong, is 2x squared plus 4 reducible over Q? Yan, mag-iiba yung sagot. No? Alam mo yung 2x squared plus 4, kahit fa-factor yan into 2 times x squared plus 2, it doesn't mean na siya ay reducible sa Q. Alam niyo bakit? Si 2 na ito is a unit in Q square bracket x. Diba? Unit kasi si 2. Ang 1/2 kasi ay rational number. Sige, I will give you some time to think about this. Why the answer to the first question is yes, while the answer to this question is no. You cannot separate 2x squared plus 4 into 2 parts so that both of the parts are non-unit. Ito kasi hindi mo na ma-split yan, di ba? Di ba? tanging paraan to split is by doing this factoring. But yet, this factor is a unit in Q square bracket X. So this is not considered a good factorization. Okay? Of course, the polynomial X squared plus 1 is, of course, napaka-classic na ito. No? This is irreducible over R. Hindi yan na-factor over R. Pero, tignan nyo to. Same polynomial X squared plus 1, na-factor siya over Z sub 2. Kasi sa Z sub 2, ang X plus 1 squared, take note, diba? X squared plus 2X plus 1 yan. Sa Z sub 2 kasi 0 yan. Diba? Okay, freshman's dream theorem. Pareho siya sa X squared plus 1. So you can factor X squared plus 1 into product of non-trivial factors, X plus 1 and X plus 1. Therefore, hindi man reducible sa X squared plus 1 over R. It is reducible, however, over Z sub 2. Ako, mukhang nagbabadyang problema ito, no? Dagdag to sa sakit ng ulo nyo, no? Kasi yung pagiging reducible at irreducible pala talaga ay depende sa kung anong ring yung pinag-uusapan. Yeah. This will be a very hard problem to solve. Kaya nga tayo merong lesson na ganito, no? How would you know in advance kung reducible or yan, ito yung remark natin. Okay, mag-alala kasi talaga namang walang nagsasabing madali ang pagdedetermine whether a polynomial is reducible or not. No? In fact, this is a well-known hard problem. Specifically, itong mga examples na binibigay ko, maliliit pa nga lang ang degree. What more, pag binigyan ko kayo ng degree 1,000, degree 3,024, yung mga ganong klaseng polynomial. Hindi naman, may awa naman ang Diyos. Charot. Hindi naman siguro tayo aabot sa ganon. No? But I want to say that if you feel that it's kind of hard, nahirapan kayo to determine whether it's reducible or not, it is true. It's not an easy problem to determine whether a polynomial is reducible or not. Kaya ang gagawin natin sa mga next few slides, we will make it a little bit easier for some of the polynomials. Ibig sabihin, para sa mga maliliit na polynomials, ang degree, kaya nating i-manage kahit pa paano. Okay? Siguro dahil 12:54 na, I don't want to start with this. Kasi ito yung susunod na lesson tungkol sa degree 2 or 3. Nag-start tayo sa mga pinakamaliliit na interesting degree 2 or 3, diba? Pero I don't want to start anymore kasi it's already 12:55. Pakitandaan, slide number 5 tayo natapos. Okay, pag tinanong ko next week saan tayo natapos, sabihin niyo slide number 5, ha? Okay ba? Okay, so if let's now stop the recording and